Hello, in this lecture we will find the area of the yellow circle. You can see in the picture a semicircle, and inside the semicircle we have the yellow circle, and the center of the semicircle is at point O, and the two circles touch each other at point P, or the touching point of the yellow circle with the semicircle is at point P. You can call point P a point of contact between the yellow circle to the semicircle, and we also know that the size of the line segment PQ equals to 7 times root 2. And let's call the center of the semicircle, let's call the center of the yellow circle M. So the center of the semicircle is M, and then we will connect together by a straight line points O and M. So actually the line segment MO is the radius of the yellow circle. I will mark it as R, small r. The reason that the line segment MO is the radius of the semicircle is because it starts from the line segment MO starts from the center of the semicircle, that is to say from point M, and ends at point O, that is a point on the yellow circle itself. And actually a radius of any circle is defined as a line segment that starts from the center of the circle and ends at any point on the circle itself. And the line segment MO starts from point M, that is the center of the yellow circle, and ends at point O, that is a point on the yellow circle itself. For that reason, MO, the line segment MO, is the radius of the yellow circle. Okay. We have a rule. I will call it rule number 1. According to rule number 1, if two circles touch each other, either internally or externally, then their point of contact lies on the straight line joining their centers. I will read again rule number 1. So rule number 1 states that if two circles touch each other either internally or externally, then their point of contact lies on the straight line joining their centers. Okay, now I will explain the meaning of rule number 1. If two circles touch each other, in our example, the yellow circle touches the semicircle at point O. The yellow circle touches the semicircle internally at point P, and actually point P is their point of contact. So rule number 1 states that their point of contact lies on the straight line joining their centers. So their point of contact lies on the straight line. So point P lies on a straight line. Which straight line? The straight line that joins the centers together. Actually, we have two centers. The center of the yellow circle is point M, and the center of the semicircle is point O, and the line segment MO joins the two centers together. And rule number 1 states that point P lies on the straight line that joins their centers together. That is to say, PMO is a straight line. Okay? Or we can say that if you draw a line between points P, M and O, then that line will be a straight line. That is exactly what rule 1 says. That point P lies on the straight line that joins the centers together. So MO is a line segment, and point P lies on the same straight line as MO. Or in other words, PMO is one straight line. Okay? So we can say that PMO lies in one straight line as MO itself. Okay? Again, if two circles touch each other, in our example, the yellow circle touches the semicircle internally at point P. So point P is the point of contact. So rule number 1 states that their point of contact, that is to say point P, lies on the straight line joining their centers. Point P lies on the same straight line as MO. Point P lies on the same straight line as the line segment MO. Or in other words, PMO is one straight line. Or, as I have already said, that if we join together, if we connect by a line points P, M and O, then that line will be a straight line. Or we can also say that point P creates with the line segment MO one straight line. Okay, point P creates with the line segment MO one straight line. So PMO is a straight line. Okay, so I'll explain again. If two circles touch each other internally, in our case the yellow circle touches the semicircle internally, then their point of contact, that is to say point P is their point of contact, lies on the straight line. Which straight line? Point P lies on straight line. Which straight line? On the straight line that joins their centers together. So we have line segment MO that joins their centers together, and point P lies on that straight line. That is to say, PMO is one straight line. Okay? So the sentence actually says that if we connect points P, M and O together by a line, then that line will be a straight line. Okay? Or you can also say that the meaning of rule number 1 is that point P creates with the line segment MO one straight line. That is to say, PMO is a straight line. Okay, or you can say that the line segment MO that joins the centers together. As you can see, M is the center of the yellow circle and O is the center of the semicircle, and the line segment MO that joins the centers together with point P creates one straight line. The line segment MO with point P creates together one straight line, that is to say PMO is a straight line. Okay, so actually we can say also that PO is a straight line, and as you can see from the picture, MP is also the radius of the yellow circle, because it starts from the center of the yellow circle, that is to say it starts from point M and it ends at point P, that is a point on the yellow circle itself. For that reason, MP is the radius of the yellow circle. As I've already told you, the definition of a radius is that a segment line that starts from the center of the circle and ends at any point on the circle itself. So the line segment MP starts from the center of the yellow circle, that is to say from point M, and ends at point P, that is a point on the yellow circle itself. For that reason, MP is the radius of the semicircle, and actually OP equals to 2 times R. OP equals to 2 times small r. That is to say, OP equals to the diameter of the yellow circle. Because any line segment that equals to 2 times the radius of the circle inside the circle is defined as the diameter of that circle. So actually OP that equals to 2 times the radius of the yellow circle is also defined as the diameter of the yellow circle. But because of the fact that OP is a straight line, we can define OP as the radius of the semicircle, because it starts from the center of the semicircle and ends at point P, that is a point on the semicircle itself. For that reason, OP equals to the radius of the semicircle. I will mark it as capital R. Okay, OP equals to the radius of the semicircle. I will mark it as capital R, because it starts from the center of the semicircle and ends at point P, that is a point on the semicircle itself. For that reason, OP is the radius of the semicircle, and for the same reason, we can also say that OQ is the radius of the semicircle. I will mark it as capital R, because it starts from the center of the semicircle and ends at point Q, that is a point on the semicircle itself. Okay, so actually we have here two equalities. From one side, OP equals 2 times the radius of the yellow circle, and from the other side, OP equals also to the radius of the semicircle. So we can say that OP equals to OP, and then we can deduce from it that 2 times R equals to capital R. Okay? I replaced OP by the value of OP in this equality, so it is 2 times R, and here I replaced OP by the value of OP on this equality, that is to say capital R. So we can say that this will be our first equation. We can say that 2 times small r equals to 1 capital R. Okay? So actually, this is the relationship between the radius of the big semicircle to the radius of the yellow circle. The radius of the semicircle is twice of the radius of the yellow circle, or 2 radiuses of the yellow circle equals to 1 radius of the semicircle. Okay, the radius of the semicircle is larger twice from the radius of the yellow circle. Okay, so we have OP that equals to the radius of the semicircle, and also OQ equals to the radius of the semicircle, and we have the second rule. I will call it rule number 2. According to rule number 2, in any circle, a radius and the tangent to that radius are perpendicular to each other. I will read again rule number 2. So actually rule number 2 states that in any circle a radius and the tangent to that radius are perpendicular to each other. In any circle, a radius and the tangent to that radius are perpendicular to each other. So actually, if we have a radius, let's call it R, and the tangent to that radius, let's call it T, then the radius is is perpendicular to the tangent, that is to say this angle equals to 90 degrees and also this angle equals to 90 degrees. Okay, so we actually can implement rule number 2 in our circles, because we have in our circle segment MO equals to the radius of the yellow circle, and QO or Q is tangent to that radius. So according to rule number 2, the radius is perpendicular to the tangent to OQ, that is the tangent to that circle. That is to say, angle POQ equals to 90 degrees. And we can also say that angle POL equals to 90 degrees. Because we have radius MO and tangent to that radius, that is QO, then we can deduce from rule number 2 that the radius is tangent, the radius is perpendicular to the tangent, that is to say angle POQ equals to 90 degrees and also angle POL equals to 90 degrees. Okay, so in any circle, a radius and the tangent to that radius are perpendicular to each other. That is to say, this angle is 90 degrees and also this angle equals to 90 degrees. Okay, so actually we have here a right triangle. POQ is a right triangle because of the fact that angle POQ equals to 90 degrees. So I will draw again the right triangle POQ. So I draw again the right triangle POQ. As you can see, side PO of the right triangle POQ equals to R, and also side OQ of this right triangle equals also to R, and the hypotenuse of the right triangle POQ equals to 7 times root 2. Okay, it is exactly as the original triangle, as you can see, and here we can implement the Pythagorean theorem in order to find out the value of capital R. And actually the Pythagorean theorem states that the Pythagorean theorem relates only to right triangles. So it states that in a right triangle, because it relates only to right triangles, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. I will read again the Pythagorean theorem. So the Pythagorean theorem states that in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So if we have a right triangle, so in this right triangle, the square of the hypotenuse, that is to say AC square, equals to the sum of the squares of the perpendiculars. AC square equals to AB square plus BC square. Okay, so it applies only to right triangles. The square of the hypotenuse, that is to say AC square, equals to the sum of the squares of the perpendiculars. AC square equals to AB square plus BC square. So we can implement this theorem in our specific right triangle. So actually here in this right triangle the square of the hypotenuse, that is to say PQ square, equals to the sum of the squares of the perpendiculars. That is to say PQ square equals to OQ square plus PO square. Okay, so in our specific right triangle POQ, PQ square equals to OQ square plus PO square. But we know that OQ equals to R and OP equals to R and QP equals to 7 times root 2. So we can substitute PQ by 7 times root 2. I will call it second equation. In the second equation we will substitute PQ by 7 times root 2. And then we can substitute OQ by capital R. And we can also substitute PO by capital R. So we will get that 7 times root 2 square equals to R square plus R square. R square plus R square equals to 2 times R square, and 7 times root 2 square equals to 49 times 2, because 7 square is 49 and root 2 square equals to 2. Okay, so I'll write it down. Okay, we got that 49 times 2 equals to 2 times R square. Now we will divide the equation by 2. We will get that 49 equals to R square. After we divided the equation by 2, we got that 49 equals to R square. Now we will take a root out of equation number 2. Okay. We will get that 7 equals to capital R. So after we took a root out of equation number 2, we got that capital R equals to 7 units, because the root of R squared is R, and the root of 49 equals to positive 7. Actually, the second root of 49, that is negative 7, is impossible in our case because we are talking about radiuses, and radius must be a positive number, so we will take into account only the positive root of 49. So the radius of the semicircle, that is to say capital R, equals to 7 units, but according to equation number 1, we know that capital R also equals to 2 small r's. So R equals to 2r, so I write the equation number 1 again. So according to equation number 1, capital R equals to 2 times small r. So we can substitute capital R by 7, because capital R equals to 7. So we got here that 7 equals to 2 times small r. We can divide the equation number 2 by 2. We will get that so we got that small r equals to 3.5 units, or the radius of the yellow circle equals to 3.5 units. Now, after we know the size of the radius of this small circle, the yellow circle, we can easily know the area of the yellow circle, because according to the formula of area of any circle, we know that the formula for the area of a circle is A, abbreviation for area, equals to pi times r squared. Okay, the formula for the area of a circle is A, the area, equals to pi times the radius squared. So we can substitute the radius r by 3.5 units in order to find out the area of the yellow circle. Okay? So I substituted R in the formula of the circle by 3.5 units, because the radius of the yellow circle equals to 3.5 units. So we know that 3.5 squared equals to 12.25, so I write it down. So the area of the yellow circle equals to pi times 12.25, because 3.5 squared equals to 12.25, and pi times 12.25 equals to the area of the yellow circle. So the area of the yellow circle equals to 38.48 units. Okay, we multiplied pi by 12.25 and we got that the area of the yellow circle equals to 38.48 units, or the area of this yellow circle equals to 38.48 units. Okay, now I will summarize the lecture. So actually we wanted to find out the area of the yellow circle, and we know that the formula for the area of any circle equals to pi times the radius squared. So we will find the radius of the yellow circle, and then we will know the area that equals to pi times the radius squared. Okay, so actually, as you can see in the drawing, we have a semicircle that its center is at point O, and inside the semicircle we have the yellow circle, and the size of the segment PQ is 7 times root 2, and the touching point between the yellow circle to the semicircle is at point P, or the point of contact between the yellow circle to the semicircle is at point P, and as I've already mentioned, O is the center of the semicircle. So we have rule number 1. First of all, we defined the center of the yellow circle as point M. Then we connected points M and O together by a straight line, and MO actually is the radius of the yellow circle, because it's line segment MO starts from the center of the yellow circle, that is point M, and ends at point O, that is a point on the yellow circle itself. For that reason, MO is defined as the radius of the yellow circle. And actually, according to rule number 1, if two circles touch each other either internally or externally, then their point of contact lies on the straight line joining their centers. So we actually in the picture you can see that the yellow circle touches the semicircle at point P. So the point of contact is point P, and according to rule number 1, the point of contact lies on the straight line joining their centers. The point of contact lies on a straight line. Which straight line? The straight line that joins the centers M and O together. So if line segment MO joins the two centers M and O together, then point P lies on that same straight line. That is to say, PMO is a straight line. Or in other words, if we connect points P, M and O by a line, then that line will be a straight line. Okay? Or we can say also that the point of contact P lies on the same straight line that connects the centers together. So if the line segment MO is the straight line that connects the centers together, yes, then point P lies on that same straight line. That is to say, PMO is a straight line. Okay, again, you can say that rule number 1 also says that if you connect points P, M and O together, then by a line, then that line will be a straight line. Okay? So actually PMO is a straight line, or you can also say that PO is a straight line. And actually we can also say that MP is the radius of the yellow circle, because it starts from line segment MP starts from the center of the yellow circle and ends at point P, that is a point on the yellow circle itself. For that reason, MP is the radius of the yellow circle. So actually OP equals to 2 times R, and that is the definition of the diameter. OP is also the diameter of the yellow circle. Okay, because any line segment in a circle that equals to 2 times the radius of the circle is defined as the diameter of that circle. For that reason, OP that equals to 2 times small r equals to the diameter of the yellow circle. And also, because of the fact that OP is a straight line, we can also say that OP equals to the radius of the semicircle, because line segment OP starts from the center of the semicircle and ends at point P, that is a point on the semicircle itself. And that is exactly the definition of a radius. The radius is defined as a line segment that starts from the center of the circle and ends at any point on the circle itself. And that is exactly line segment OP, that it starts from the center of the semicircle and ends at point P, that is a point on the semicircle itself. For that reason, OP is also defined as the radius of the semicircle. So we have here 2 equalities. From one side, OP equals to the diameter of the yellow circle, that is to say OP equals to 2 times small r, and from the other side, OP equals to the radius of the semicircle. From that 2 equalities, we can deduce that 2 times small r equals to capital R, that is the radius of the semicircle, or 2 times the radius of the yellow circle equals to 1 time the radius of the semicircle. Or the radius of the semicircle is twice than the radius of the yellow circle. 2 times larger, the radius of the semicircle is 2 times larger than the radius of the yellow circle. Okay? And actually, so OP is the radius of the semicircle. We defined this as capital R, and for the same reason OQ is also the radius of the semicircle, because it starts from the center of the semicircle. That is to say, it starts at point O and ends at point Q, that is a point on the semicircle itself. For that reason, OQ is defined as the radius of the semicircle. So we have here 2 radiuses of the semicircle, OP and OQ, and according to rule number 2, in any circle, a radius and the tangent to that radius are perpendicular to each other. So if you have a radius, we call it capital R, and the tangent to that radius, we call it capital T, then the radius is perpendicular to the tangent. That is to say, this angle is 90 degrees and this angle is also 90 degrees. So we actually can implement rule number 2 in our circles, because we have in our circle MO, line segment MO is the radius of the yellow circle, and we have tangent to that radius, that is QO. QO is the tangent to the radius MO. So because of the fact that QO is tangent to the radius MO, we can implement rule number 2 here, and we can say that the radius is perpendicular to the tangent. That is to say, POQ equals to 90 degrees, and also POL equals to 90 degrees. So actually, we have here a right triangle. POQ is a right triangle because angle POQ equals to 90 degrees. So I actually draw again the right triangle POQ, and in the right triangle POQ, OP equals to capital R, OQ also equals to capital R, and the size of the hypotenuse in this right triangle equals to 7 times root 2. So we can implement the Pythagorean theorem in order to find out the value of capital R, and the Pythagorean theorem states that in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So if this is our right triangle, then AC squared, the square of the hypotenuse, equals to the sum of the squares of the perpendiculars. That is to say, AC squared equals to AB squared, or plus AB squared plus BC squared. Okay, so in our specific right triangle, we can say that the square of the hypotenuse, that is to say PQ square, equals to the sum of the squares of the perpendiculars, that is to say PQ square equals to OP square plus OQ square, or as you can see here, PQ square equals to OQ square plus PO square. but we know that OP equals to capital R, PO equals to capital R, and the hypotenuse PQ equals to 7 times root 2. So we can put the data in equation number 2, and we found out that the value of the capital R of the radius of the semicircle equals to 7 units, but according to equation number 1, the radius of the semicircle is twice more larger than the radius of the yellow circle. Capital R equals to 2 times small r. So in the equation number 1 we can substitute R by 7 because capital R equals to 7, and then we found out that small r equals to 3.5 units. And after we know the radius of the yellow circle, we can easily know the area of the yellow circle, because the area equals to pi times the radius squared. So we substituted in the formula of the area of a circle that A equals to pi times r squared. We substituted r by 3.5 units, and we got that the area of the yellow circle equals to 38.48 units, or the area of this yellow circle equals to 38.48 units. Okay, thank you very much.